So this is talk about a subject that's been very dear to my heart for the last 10 years. And I'm going to give you a little bit of a tutorial mixed with some research, trying to gather some enthusiasm for this type of imaging, because I think it has great potential, and it really is inherently signal processing off of data that we already have. So I'm going to talk a little bit about why we may want to have deformable models, and I will introduce to you elastography, mainly ultrasound, even though it is done for MR. And we'll give you some ideas of how you might use this technique for cancer detection, and discuss a bit future research on this. So everybody who's been to the doctor knows that elasticity and pathology correlate. Okay. I'm quite sure that after spending 6 months in France, my liver got a lot stiffer than it was before. And in general, if you look at how breast cancer is detected, you feel for lumps. The famous DRE for prostate cancer, this is all palpation. But what is palpation? Palpation is really a very coarse and approximate in terms of location and quantification of elasticity. So you want to correlate it with pathology, but you can also use it for segmentation. And I have here an image of the prostate, an elastography image of the prostate using MRI and one using ultrasound. And you can see in the ultrasound image, you can barely see the border of the prostate, but you can see it very well in the elasticity image. So it allows you to have a registered, naturally registered way in which you might segment things. Then it's also very useful for deformable registration. Okay, everybody talks about deformable registration with an elastic potential, in which you have Lamé parameters, but you don't really know what they are. But in many cases, you actually have those and can measure those. So why not measure them and use them so that you can deform a source shape into the target shape with the appropriate values of registration. And finally, what I think is going to also be a huge hit is the fact that elasticity is common across modalities. Okay, so if you find elasticity in MR and you can image it well enough, and you find it in ultrasound, then you can use elasticity as a way of registering those images. You don't need to look at mutual information, you don't need to look at feature points and so on. I think that's very exciting to me. Now, there are a lot of procedures in which tissue deformation can affect accuracy. Here's, for example, what a radiation oncologist sees, okay, when they insert a needle into the prostate in order to drop radioactive seeds as part of an alternative treatment for prostate cancer. And you can see that because of the needle being poked through this template in the prostate, okay, everything moves, okay? And what they need to do is they need to maneuver the needle and the bevel in such a way that eventually the needle tip appears as an artifact, okay, at the expected location on the grid, okay? So in order for us to understand how tissue gets deformed, okay, when you actually poke a needle through it, it would be really required for us to know what is the underlying mechanical properties. Okay? So, very simple. I'm sure everybody who's been in a surgery and they've looked at the open abdomen has had this irresistible temptation to try and jiggle the liver. And this is exactly what you're trying to do with elastography. So let's have a look at couple of tissue mimicking phantoms. Okay, the B-mode images are on the left. Okay, and you see that even though you have enclosures in these phantoms, which is rectangular in the phantom at the bottom and circular in the one at the top, the B-mode image gives you exactly the same thing. So what you can do is you can take the ultrasound transducer and slightly compress the tissue, okay, in such a way that the RF line that comes back to you, okay, will be modified because the tissue that is stiffer, okay, compresses less than the tissue that is softer. Okay, it's like having 3 springs in series. Obviously, the stiff one will compress less. So you can take the differences between the images, okay, and you can obtain a strain image which actually shows you much more detail than you would have expected from the B-mode image. And that strain will show that it's lowest strain within the circular enclosure, okay? So the difference between uncompressed and compressed will be higher, okay, outside the stiff region than it is within. And that makes perfect sense. So in general, when we talk about elastography, we have several stages of solving the problem. We apply a compression to tissue. We look at that, we image that tissue to get the internal strain or displacement. Okay, then we use this displacement into an inverse problem, okay, in such a way that we recover the enclosure, okay. And there are many ways in which you can apply the excitation. Here is a shear wave propagating through tissue. You can see that the wave actually speed up in the stiffer region, as you'd expect, okay, for them to do, and therefore the wavelength increases. So you know there's something there, but in order for you to actually image that correctly, you need to solve an inverse problem, okay. So let's walk through the steps that are involved, okay, with ways of providing this mechanical excitation, okay, ways of extracting the displacements, and ways of solving the inverse problem. So the mechanical excitation is fairly simple. We have here a relatively rough embodiment in which we have taken a voice coil, which basically moves up and down and responds to a red current going through it, interacting with the blue magnetic field here. And what we do typically is we use the magnets, we move the magnets and keep the coil stationary, so you have inertial forces that appear, and you can generate vibrations that are similar to what you get from your cell phone at the transducer face. Okay, you can use you can use your hand to compress, or you can use a tool such as a needle. So if you're looking, doing a procedure that's under ultrasound guidance, you could use the needle to move the tissue around a little bit, or you could use an RF ablator tool to do the same, or you might even think about a way of having a patient inside the MRI and using a pneumatic cushion into which you send waves to generate this type of vibration. Not very hard. Possibly the best way to do this, because it's easy, especially if you don't have the requirement of going very deep, is acoustic radiation force. Okay, so if you have here the face of a transducer, and if you focus the waves by adjusting the delays so that they all arrive at the focal region at the same time, okay, and you maintain the excitation for a much longer time that you would use with normal conventional ultrasound imaging pulse. Okay, you actually get a pressure, acoustic pressure. Okay, so I'm not sure whether the volume at our disco night was strong enough for you to feel the sound through your abdomen. I've been into into clubs where you basically feel the radiation force quite easily from the speakers. That's the same thing really with ultrasound. Okay? And you can have this type of mechanical excitation in an MR system by using voice coils in the scanner room, which you activate in concert with the MR acquisition, so you have to modify your pulse sequence to be able to do that. Or you can use piezoelectric actuators, or you can do what we have done at UBC after a decade or so after people at Mayo did a pneumatic transmission. You basically have a big pipe from the console room into the scanner room, and that pipe transfers vibrations from a big shaker or a speaker to the patients. Here's an example of how you see the strain, okay, as a result of the natural body excitation. So we image here a region which is fairly close to the carotid, okay, and you can see the flashes that basically very neatly are in concert with the heart rate, okay? You see that. So internal body motion can also be used for the excitation. So I don't have much explicit material, but I have some here. So let's look at what kind of tissue motions can we have in tissue. And we model this as an elastic isotropic solid, okay, as described by Navier's equations, okay, where we have the Lamé parameters, and you're typically interested in the shear modulus, which has a storage component GD and a loss component GI. Okay, so you can do a Helmholtz decomposition of this equation, okay, by defining two potential, a scalar potential and a vector potential that split your displacement into dilatational and a rotational or equivoluminal part, okay? And you get, corresponding to this equation, two potential wave equations, okay, which correspond to shear motion and dilatational motion, okay? So when you actually apply an excitation to tissue, okay, you would have two types of waves traveling, okay? One which is the P wave, in which the motion is pretty much aligned, the direction of the particle motion is pretty much aligned with the direction of wave propagation. And you have a shear motion, okay, in which the particle motion is pretty much orthogonal, at least in this example, orthogonal to the wave propagation. And you note that shear waves, okay, propagate a lot slower, the order of less than 20 meters per second, versus the dilatational waves which propagate at high speeds, 1,000 meters per second and above. And this is because the Lamé parameters lambda is typically much, much larger than mu. So P waves in incompressible materials, and tissue is more or less incompressible, okay, cannot be imaged by ultrasound, okay, since they travel at the same speed. It's like, you take a rod of metal and you hammer it at one end, and then you try to hammer it again to see how the first wave traveled. You can't do that, okay? But the shear waves, the equivoluminal waves, are slower. And what it took me a while to understand is that these equivoluminal waves, okay, which I'll call shear waves, in fact, they can be polarized longitudinally, okay, so they travel in the same direction as the direction of the wave propagation, okay. So here's an example of what happens when you apply boundary condition to a tissue phantom and you send a wave through it, okay. You get a single wave propagating, okay, which is the P wave, okay, and which travels essentially at what the speed of ultrasound to be, the 1540 meter per second that you're familiar from your courses, okay. If you look at what happens at a phantom which is not constrained, okay, with boundary conditions actually allows it to move. You have a first very fast wave, okay, the same as the P wave, and after that you will have, in the same direction, a slower wave, which is the shear wave, okay? So what you can do is, you can send the shear wave to tissue, and while it travels, you can send many P waves to see how exactly it travels, and you can do that with speckle tracking, okay? So, elastography is not that new anymore. The first papers come from Kevin Parker's group, okay, in the very late 80s, okay, where they use a vibrator and they put the transducer, ultrasound transducer, into Doppler mode, and then they image the velocity field, okay? And then after the papers from Kevin Parker's group, Jonathan Ophir realized that you can do this by using processing of the RF data itself and generate a static or quasi-static strain, which was much easier to produce and reproduce than the Doppler images. So everybody refers to this, to Jonathan Ophir as the founder of the field, who coined the term elastography. But Kevin Parker had just as much to do with it at the beginning of the field. Then MR elastography was first performed in Dick Eamon's group at the Mayo Clinic. There is a paper in 1995 in Science in which they used motion encoding gradients to map the motion field through a phantom excited by a 500 hertz speaker, and their work is widely cited in the imaging world. There's been a very big contribution from a French group, from Mathias's Fink group from the Laboratoire des Ondes Acoustiques in Paris. They were really the first one to understand this phenomenon of longitudinally polarized shear waves. So they used this two ways of propagation of wave, okay, with a new ultrasound system which had parallel receives. So you get all the channels at the same time, so that you can actually monitor a wave displacing longitudinally across your transducer. So this concept was commercialized by, very successfully in a company called Ecosens, in which there is a single imaging crystal, just one crystal, not an array, okay, which sends a shear wave through the liver, okay, and you can monitor the velocity of the shear wave, from which you get the shear modulus, and that shear modulus has been shown in many studies to accurately determine the level of fibrosis in a liver. So there's no reason why this system cannot be made small enough so that when I travel to France, I can actually monitor my stiffness and see how much red wine I can drink. So I'm looking forward to that. So this concept was also commercialized from Fink's group in a company called Supersonic SSI. Supersonic shear imaging is the imaging they have. And what they do is they apply an acoustic radiation impulse force along a line in the middle of the transducer, so that they generate a conical wave that travels from the middle of the transducer outwards. And because they have parallel receive for each of the channels of the transducer, they can monitor how the wave propagates. Okay, I have a video of that. Okay, so I'm supposed to go to 50. So this is shear wave mode, and you see here what happens. There is multiple RF pulses in the middle of the transducers. They generate a laterally traveling wave, which actually images the images the lesion, okay? And from the speed of that traveling wave through the lesion, you can get the shear modulus, and that shear modulus has been shown to be a bit helpful with the BI-RADS classification when people are looking for cancer. I have to be very careful what I say here with Mike Brady being in the audience. So there are many groups working in this area. You'll have this if you want to look for what they do with a copy of my overhead, so I'm not going to spend any time on this. Okay. So let's move on to tissue motion estimation. Okay. There are really just two common ways that are used for elastography imaging. It's ultrasound and MR, okay, because they don't have ionizing radiation, okay. In ultrasound, has the advantage of being inexpensive and accessible. Disadvantage is that it's less accurate tissue displacement tracking, and really only the axial direction along your transducer is accurate. Everything else is not that accurate. MR uses motion-sensitive phasing coding, okay, to get displacements, and it has a huge advantage of being able to give you a 3D, full 3D vector displacement over a 3D volume. But it is significantly slower, and that is an issue, because if the examination times takes an hour, it's very difficult to see, to be convinced that you get the shear wave motion from the same location. Displacements. When we started to work with elastography, we started looking at B-mode images that basically get the envelope of the RF data, not the RF data itself. We thought that by reasonably clever motion tracking, we can get high enough accuracy. That turns out to be false, so we had to move to RF data. And then you use standard cross-correlation techniques. You define your RF line at 2 compression instances. We call that a delay, really. There are 2 compression instances. And you slide that window atop your reference, and you find the point of maximum correlation, and that gives you the displacement. Okay. We started that and produced actually some software by exploiting the continuity of motion, okay, to reduce the search range that we had to do to find the maximum of the NCC. And we really had the first clinical real-time elastography system available on ultrasound machines, and we did this with ultrasonics. And you see that when you actually move the transducer on top of a phantom, at the beginning you really don't see anything, but the features appear from the strain. Okay, now what is really difficult with a standard machine is to actually get a very high frame rate. So, you know, the imaging frame rate for a full frame of ultrasound is somewhere between 20 and 60 hertz, okay? So if we want to increase the frequency of the shear waves that we monitor with ultrasound, and avoid aliasing, we cannot scan the full image, okay? What we need to do, because if we scan the full image, you clearly get aliasing of the RF, of the motion that you're trying to capture. So what we were forced to do is look at using multiple sectors, okay, which we image one at a time, and we can image these at much higher frame rate. And what we do then is we stitch together the adjacent sectors. We compensate for the ultrasound delay for each scan line. Then we compensate for the delays between the sectors, okay? And when we do that, we can reconstruct the probe motion. So here's, for example, the motion in tissue before our compensation. If we use a sector-based approach, then we can seamlessly get a very high frame rate that can capture tissue motion. We spent a very long time, close to a year and a half, trying to achieve this, and then one of my students, a lone Muslim student left at Christmas by himself in the lab, he came up with this bandpass sampling idea. Aliasing happens when you actually don't know what is the rough frequency of your signal. We have an example here of two sinusoidal that are fitted to sinusoids, three sinusoids that are fitted to the same data set. If you do know that you're looking into a higher frequency range, then what you can do is you can use the communication concept of bandpass sampling to beat down the frequency to DC. And then we have essentially obtained similar sampling of harmonic and multi-frequency motion using bandpass at 50 Hertz than we get with a standard rate at close to 350 Hertz. You can do this by using axial motion at slightly different angles to get both axial and lateral motion, which you can then, you get axial motion along two beam angles, which you can then combine into a single axial and lateral motion, which gives you a 2D motion field. Much harder to come up with direction of motion in the elevational direction, okay, because you're really not monitoring the motion fast enough. So for lateral motion, you need access to something like the Philips X matrix 2D array that has high frame rate in the elevational direction as well. So we can generate waves with MR as well using motion encoding gradients. This is a wave image through the liver. Here are corresponding images that are obtained through ultrasound. So they are fairly similar from MR and ultrasound. Okay. So now we can start looking at some inverse problem. Okay, so the first thing that we note is that a first approximation to the elasticity is the inverse of the axial strain. Okay, but unless you know the force with which you can compress, there's no way that you can recover from that a quantitative absolute value of elasticity. So this is still very useful for real-time imaging. Okay, it's just that you can't bring a patient in January and then 6 months later and compare the two images and say, yeah, tumor has grown because it's stiffer in a larger volume than it was before. Okay, the other way in which you can get a fairly easy idea of the stiffness is through what is called local frequency estimation. By knowing the excitation frequency, you can recover the wavelength, and from the wavelength you can get the shear modulus. Everybody assumes that the density of tissue is that of water. So these are the two easy ways. We've contributed towards this by looking not just at a quasi-static or harmonic excitation, but trying to do a broadband excitation. If you do a broadband excitation, you can think that a tissue patch can be taken as a reference, and then you can compute a transfer function the same way you would get a transfer function of an acoustic amplifier as a curve, okay, in the frequency domain, and that curve can be measured over the entire space that you are monitoring, and you can produce some type of a norm of the on that transfer function and produce an image which is not just quasi-static, but it is a more stable image of relative tissue motion. Now, if you endow this transfer function with a specific model, okay, for example, you give it a time constant, then the phase of the transfer function corresponds to relaxation time. Relaxation time corresponds to viscosity. And this is important, okay? Viscosity is important, not if you're Homer. Here we have an example of him visiting his doctor for his regular checkup, and they're doing a test on him. in which they're looking at the settling time of an excitation through his stomach, and here it goes and goes, and then Homer is very proud of it, and the doctor says, "Oh, nurse, cancel my 1 o'clock because it never stops." So viscosity is important. Here we have a phantom which has a stiff enclosure and a stiff and more viscous enclosure. And if you look at the images of transfer function through tissue, these two enclosures will exhibit different frequency response. And from the relaxation time information, we can get a contrast which is viscosity specific. So if we look at the phase of the transfer function, we see that we get the more viscous disclosure. Enclosure. If we look at the magnitude, we get both the viscosity and the stiffer enclosures. And another beautiful thing about using a transfer function is that when you compute a transfer function from real-time data, you can compute something which is called a coherence function, which is based on the fact that the linear system, when you tickle it at a frequency which is 7.2 hertz, okay, you expect all the excitation to come out at 7.2 hertz. Okay, the coherence function quantifies the frequency spill. Okay, what comes out at 5 hertz instead of 7.2 hertz? That gives you an idea of whether your tissue is linear and whether your SNR is good. Now, strain images suffer from artifacts, okay? These are caused by two things. They're caused by boundary conditions, okay? So if I press a phantom which has a stiffer and a more viscous inclusion, with a wide plate or a narrow plate, the response is not the same, okay? So strain would be very, very much dependent on excitation, and neither the real part or the imaginary part of the strain really are, they're not uncorrupted by each other. So you can't really, you see an amount of stiffness in what you'd expect to be viscosity image and vice versa. So really you have to do a full modulus reconstruction based on an inverse problem to get that, okay? So we solve an inverse problem by taking a finite element model of the tissue. What leads to the finite element model depends on your assumption. If we just take a shear wave equation, okay, corresponding to the shear wave potential, okay, you get a wave equation. The wave equation is discretized into an MBK system by finite element method. And this system is actually linear in the shear modulus. And therefore, you can recover the shear modulus by solving this discretized linear system in a region of interest in which you assume that there are no external forces applied, okay? And because of linearity, we can solve this with some regularizing term. Problems are as follows. We have a very large number of parameters, okay? We suffer here from the same curse of dimensionality that people have when they move to this type of problem. We tried various types of regularizations, and we found that the sparsity regularization works the best. Okay, so we use a discrete cosine transform for that in order to reduce the number of shear values, shear parameter values that we solve for by multiplying A with a very tall matrix R star. Okay, now the accuracy that you get depends on the complexity of the models, okay? If you allow the pressure to vary within the Navier's equation, you get much better results, as Park and Maniati have shown. If you eliminate the pressure by taking the curl, then you get an accurate representation of your motion. And finally, if you actually remove the homogeneity assumption, so you do not assume that tissue is locally homogeneous, and take the curl, you get vast improvements over the shear wave equation model. Okay? And this is how a typical reconstruction might look. This is an MRE phantom data, okay, that has several inclusions. Okay? These are all provided by the manufacturer. And these are the waves that we get in the X and Y and Z displacement. And here is the reconstruction that you get from it. Now, when you assume that you do not have homogeneity, then you can take a very fancy Agar phantom, which is plastered with inclusions all over the place. Okay? You can see where these inclusions are by taking a T2 image. Okay? And you can see that the local frequency estimation gives you a very sorry representation of what the T2 image tells you about the enclosures. Okay? And if you assume homogeneity, as done in this curl-based inversion, you get much worse results than by using the inhomogeneous finite element method that we currently employ. We've done similar inversions based on for in vivo for the prostate, and I'm showing you this slide to show you that the inverse problem is far from being solved. Okay, the Mayo approach, which is the LFE, okay, at the frequency range that we're able to excite the prostate, gives us pretty sorry data. The mixed FEM by Park-Magnati seems to give us reasonably decent contrast, but if you compare that with a different model of FEM inversion, you do not get, you get some similarity, but not something that will allow you with confidence to go to the FDA and say, here, I solved the problem of tissue elasticity measurement. I have the one way which gives us tissue elasticity in kilopascals, which is why I think we're still struggling pushing some of the quantitative elasticity imaging through FDA. Here's how this looks in a real-time implementation. This is the linear array with a shaker at the back. This is used now in 2D to image lesion in a breast phantom. Okay. Our system, which has a GPU implementation, provides us with the B mode, with the storage modulus, loss modulus, and the coherence function that gives you a measure of image confidence at the same time. Okay. We also have this done with a 3D transducer. This is the same phantom that you've seen imaged with MRI. And here's one of the 3D enclosures. You can barely see it with the B-mode image, but this color image actually gives us the elasticity in kilopascals according to our color map. We can map hard inclusions or soft ones. And this system is available across several platforms now, including our B&K system. Okay, so I'll tell you a little bit about the prostate images that we've gotten with our transducer. We've used two types of vibrations. Okay, we have equipped our robotic transducer that you've seen in my previous talk with a shaker which provides real-time controllable strain. We also have a shear wave exciter which goes against the perineum of the subject. And some of the image here, they're shown qualitatively. You see much, much better internal contrast of the prostate than you get with B mode, okay? You see internal structure, the prostate central zone, okay? You see the ejaculatory ducts. You see the prostate boundary, and the darker areas are areas of higher stiffness, which correspond to cancer in many cases, but not all. Okay, so our system provides a map of elasticity in kilopascals, and you can see this is the same sagittal imaging plane that we've used with the Da Vinci, but now it is endowed with a absolute value of elasticity. We have now a few papers out that actually look at the correlation between stiffness and cancer. Prostate is fairly difficult to handle. If you use a multi-parametric approach, we can get decent AUCs of around 0.82. But I have here two instances in which you have much stiffer regions that do correspond to cancer. And we have here one region of which is much stiffer that does not correspond to cancer. Okay, so this is still something to be studied. But if we use multiple parametrics, we get AUCs that are quite respectable, not quite as good as MRI, but this is our studies are still fairly new. Okay, so I also will show you some images of the prostate. These are waves propagating through the prostate. These waves are generated by transperineal exciter. These correspond to the waves that are monitored by MR. The excitation that we use is transperineal. The subject stays inside the MR with the legs slightly spread apart. Okay. And what we have is a shaker which pushes against the perineum and sends waves. These waves can then be resolved by an inverse problem into a shear modulus and loss modulus, which then is completely registered to the T2 image, and we can look at correlation to histology. We've done quite a bit of work to make this correlation proper. That is, most studies will look at a region that appears to be stiff, and if they find it the same quadrant of the prostate cancer, they say, whoopsie, this is great. We haven't done that. We've actually done a volumetric map of the pathology. We register volumetrically the ultrasound to the pathology, and we measure our AUCs based on this study. So I have just a few more minutes to talk about other exciting application of elastography. Here's a case of deformable registration. How we do this is not that important. We decide here to apply a pressure that is internal to the intersection of surfaces to bring them into registration. But if you apply a relatively low Poisson ratio and Young's modulus, what happens in the deformable registration is you get a beautiful matching of the surfaces that you're trying to match, but the inside, okay, the urethras corresponding to the MR and ultrasound registration are off by quite a bit. If you use physical parameters that are derived from elastography, then you tend to reduce the error, the internal error, even though the surfaces may not be matching just as well. And we have a first instance in which we actually have done MR to MR registration in order to register pathology to in vivo MR. And we have one step which does just a region-based intensity functional minimization that is actually regularized by an elastic potential derived from a magnetic resonance elastography to have deformation which is actually consistent with the elasticity distribution of the organ. I mentioned to you that you can do segmentation. Here's an MRE derived image of the prostate with a simple segmentation algorithm that doesn't require any type of initialization. Okay, that's again based on elastography. And here's a pretty lousy looking B-mode image that we have used with Chan Vesey to get again initialization-free segmentation of the prostate solely based on the elastography images. So there's a lot of potential for image guidance, and we can use this for also for simulation and treatment planning. Okay. So to conclude, I think elastography is really exciting biomechatronic problem. It involves everything: actuator design, pulse sequence design for MR, RF data measurement for ultrasound, beamforming, and all sorts of neat things. But in general, it requires small equipment changes, and it can be implemented on a standard ultrasound and MR machine. It can be used for finite element deformation models, which are useful for registration, for segmentation, and for path planning. But there's also huge potential for imaging for pathology, and especially cancer. So I didn't have time to go through this, but we also have 55 patients that we've imaged for with breast elastography, and we're just about to start a liver study. There are lots of work to do in understanding what does elasticity mean in vivo, okay? Fantastic new work from Duke and other places which are looking at the elasticity of cardiac tissue, for example, during heart beat, okay? And you can see a difference in elasticity with RFI as the heart beat. This can replace much more invasive ways of measuring this. When you measure the elasticity of the kidney and you do it in systole or diastole, you don't get the same numbers. The same applies for the liver, I assume, but for the prostate it's a bit less vascularized. It's not the same issue, but certainly ex vivo imaging and in vivo imaging have nothing to do with each other, because the pressurizing an organ clearly changes its stiffness. Okay? And there's lots of interesting work that can be done in inverse problems. If you want to sink your teeth into something that, you know, is three-dimensional, and we talk about 20,000 parameters, in order to get it in real time, there are some challenges of all kinds there. So I'd like to thank you for your attention, and I'm gonna be waiting for my reading group, and I can answer some questions now. Thank you.